So I now want to discuss how it is that Hamiltonian mechanics leads us naturally to quantum mechanics, okay? So we're going to start discussing what the recipe called canonical quantization. And to do that, I want to reformulate the description of Hamiltonian mechanics that we've had so far. And to reformulate it, I want to consider some observable in classical mechanics. So let's call it O for observable. And it depends on X and P, but it's got no explicit T dependence. So it only depends on T because it depends on X and P, and X and P themselves depend on T. Now let's calculate what is the time derivative of O and X and P. Well, this will be equal to dO dx times by x dot. So that's taking care of the time dependence because x depends on time. And then plus dO dP times by p dot. Okay? And now I'm going to use Hamilton's equations to rewrite this as dO dx, and then x dot is dH dP, and then we will have minus dO dP, and the minus sign comes about because P dot is minus dH dx. Okay? Now, this is a very interesting structure that I'm getting here, and I'm going to give it a name. So if I have got A, comma B, and I've got these curly brackets, this is defined to be equal to dA dx dB dP minus dA dP dB dx. And this is called a Poisson bracket. Okay? So this is just a definition of what I mean by a Poisson bracket. And then the dO dt is simply given by the Poisson bracket of O with the Hamiltonian. Now, this curly bracket that I'm using for the Poisson bracket, it's often used in quantum field theory also for the anti-commutator, okay? So I do not mean the anti-commutator at all. When I write these curly brackets here, I mean the Poisson bracket, so exactly what is written in the square box. So here is my reformulation of classical mechanics. So I'm going to say, so this is a reformulation of Hamiltonian mechanics. I'm going to say we are given the Hamiltonian as a function of P and X. And I'm going to tell you that the dynamics is dO dt is equal to the Poisson bracket of O with H. Okay? Now, you might say to me, no, don't do this. You know, we've lost Hamilton's equations 3 and 4. Well, let's check and see if we've lost Hamilton's equations or not. So what is x dot? That is dx dt. So let me plug x into the Poisson bracket. So just plugging it in, I'll have dx dx, dH dP minus dx dP dH dx. And we know that dx dP vanishes. So this is equal to dx dx, which is 1 times dH dP. So x dot is equal to dH dP, and we've reproduced equation 3. That's the first of Hamilton's equations. Next, let's calculate dP dt. Again, just plugging it straight in. This is dP dx. I'm just using the definition of the Poisson bracket. Minus dP dP dH dx. And now, this first term vanishes because dP dx is 0. So what do I end up getting? Well, I've got the minus sign and I've got dH dx. And you can see that I've now reproduced equation number 4, which is the second of Hamilton's equations. Great. So in fact, I do have Hamilton's equations of motion, and this is a very nice, efficient way of discussing the theory. Given the Hamiltonian, h of p and x, written in terms of the Poisson bracket, let's leave the Poisson bracket exposed, and the dynamics for the ODT is just the Poisson bracket of O with h. Now let's work out a few things. So first of all, what is the Poisson bracket of x with p? Well, if I just plug it straight in here, okay, let's look at the square bracket at the top. dx dx is 1, dp dp is 1, minus dx dp is 0, dp dx is 0. So this is 1 minus 0, so I just get 1. I'm just substituting things into the Poisson bracket formula. Next, let's calculate what is the Poisson bracket of p with x. Well, the Poisson bracket of p with x, dp dx is 0, dx dp is 0, minus dp dp is 1, dx dx is 1, so it's 0 minus 1. This is minus 1. Interesting. xp is minus px. In fact, let's calculate what is ba. Okay, that Poisson bracket. Well, this is equal to db dx dA dp minus dB dP dA dx. So look at the formula that I've just written down. dB dx dA dP was a plus. Well, that was the minus term inside the boxed equation at the top of the page. And dB dP dA dx, that was the term with the plus on the top of the page. So looking at the formula I've just written down and looking at the formula at the top of the page, we learn that the Poisson bracket of A with B is minus the Poisson bracket of B with A. Well, that's an interesting formula. Now I want to calculate one more Poisson bracket. Let's work out what is the Poisson bracket of, let's work out what's the Poisson bracket of AB with C. Okay. Well, this will be d by dx of AB, dc dp, minus dab dp dc dx. Okay, I've just used the boxed formula. So to calculate a derivative of a product, well, this is pretty easy. I'll just use the product rule. So this is just dA dx. I've got dc dp, and let me put down the b, plus, and now I won't differentiate the a, but I will differentiate the b. Okay? And then we've got minus. So I'll differentiate the a with respect to p, and I will leave the b alone. And then next time, I'll leave the a alone, and I'll differentiate the p. And if you again look at the box at the top of the page, so on your page, I'm sure you can see the whole thing together, and identify this, well, what have I got here? I've got the Poisson bracket of A with C multiplied by B plus A multiplied by the Poisson bracket of B with C. Okay, so let me rescue that formula. I want to keep it. The Poisson bracket of AB with C is equal to, I've got the Poisson bracket of A with C times by B plus A times by the Poisson bracket of B with C. Good. Okay, so, we've derived a few formulas for Poisson brackets. There's a whole lot more that you could derive, but maybe this is enough to illustrate the point. Okay, and here is the point. Okay. So far, I have just been calculating Poisson brackets in classical mechanics. What I now want to do, I want to calculate some commutators in quantum mechanics. Well, if we calculate the commutator of operator X with operator P, we know that this is equal to IH bar. The commutator of operator P with operator X, well, that's equal to minus IH bar. Also, if I've got two operators, A and B, and I calculate the commutator of A and B, that's minus the commutator of B with A. And then also, remember the product rule that we derived. We said the commutator of AB with C is equal to, well, leave B alone. So we've got the commutator of A with C times by B, and then plus, now leave A alone and calculate the commutator of B with C. Good. All right, so now we're going to draw some conclusions, but let's do that after a short break.